Hi, my name is Katie.
I'm Natalie.
I'm Anna.
And I'm Jenna. Our project is called WeMoove, where we use computer vision techniques and physical therapy so that we can help you move.
Today we're going to go over why this matters, our method, our results, and then the limitations, implications, and next steps for our project.
Solve is about adherence to physical therapy training. Over 50 million Americans seek physical therapy every year, but only about 35% of PT patients adhere to their assigned plan. We aim to use computer vision to partition each exercise movement into more easily digestible chunks.
The first step of our project was feature transformation. We used open pose to get the XY coordinates of each pose in each frame. We wanted an algorithm that could map similar poses and gestures to the same values, regardless of camera angle or relative location of the person to the camera. We took inspiration from SIF's usage of elimination gradients so that our model would not unintentionally focus on the individual's location in the camera view, and so that it is invariant to the user's height and distance from the camera. To implement this, we transform our features from the absolute X and Y positions to angles between detected key points. This ensures circular motions count as one movement and also allows the model to differentiate between the right and left sides of the body.
Our algorithm for extracting poses and gestures is inspired by the Harris corner detector. However, unlike a corner, which only has two dimensions, X and Y, a pose or gesture would have as many dimensions as there are angles. Additionally, poses would have a lower angle gradient, being analogous to a flat area within an image. The pictures and video on the right demonstrate how the body angles and poses have lower gradients, and how the poses are captured when the dancer slows her movement. Thus, to extract poses from angle gradients, we actually apply non-minimum suppression instead of the Harris corner detector's non-maximum suppression, after calculating the Euclidean distance between the angles and adjacent frames. Finally, we use three versions of Euclidean distances for 1. Identifying poses and gestures and also suppressing the non-maximum minimum cases. 2. Calculating a quantitative score for the patient's performance relative to a physical therapy video. And 3. A modified combination of floored angle gradients and weighted Euclidean distance. The third modified Euclidean distance formula made our model more tolerant of minor differences in absolute position, camera angle, orientation of the subject, thus leading to more detections of our specified pose across our video database.
Here are some examples of the matched poses. We took poses from the physical therapy videos and were able to match them to similar poses in dance. Our model is able to identify distinct poses, but will still group them into similar gestures. This allows the patients to isolate a specific body movement and find other videos that exercises the same body part. The poses are different, but they exercise the same muscles, which is useful for diversifying the exercise a patient has, which promotes engagement.
The accuracy score is given based on how accurate the user is to the practice video, which we obtained from Cornell University's Cornell Health site. These are real physical therapy videos prescribed for patients to follow. We tested our algorithm by recording ourselves following these and then inputting both videos to our model. We saw that videos followed along well yielded a high accuracy score, and those that were not followed along very well yielded lower scores as expected. Users can customize how their scores are calculated based on which body part they want to focus on. For example, if a patient had an arm injury, they could customize the model to focus on their arm movement and thus fit their needs. There are also 3 modes, easy, medium, and hard, that the user can select, which works by defining a threshold for the angles calculated.
To conclude, we were able to successfully utilize computer vision techniques to create a program tailored to improve patient adherence to recovery plans in physical therapy. Although we believe our project proves great progress, it did come with its fair share of limitations. For example, the camera angles between the videos must be the same, otherwise the scores will not accurately reflect their performance, as well as open pose at its own time bottleneck. Due to our restriction with GPU access, we were forced to downscale the data we processed, either through resolution or duration. Downscaling the resolution proved to reduce the most time, however, it also produced questionable key points. Thus, for the purpose of testing, we were forced to process shorter videos at full resolution.
For future implementations of this project, we would focus on 3 things: matching movements so that users can find videos of certain movements, not just poses, generate difficulty levels for exercises so users can choose a level which suits them, and finally, expand the scope of the project to also analyze other physical activities such as dance or martial arts.